Okay, I'm going to do the other homework problems for this week. So we've got another spring type question here. This one, we've got a box that is attached to a horizontal spring. So here's our box. It's attached to a horizontal spring. And this has a spring constant of 2,500 newtons per meter. We're going to pull the box 12 centimeters from equilibrium. So imagine your spring is just relaxed here, and then we're going to pull on it and we're going to displace it 12 centimeters. We're going to stretch it 12 centimeters from its relaxed position. We want to know what is the maximum kinetic energy here. Okay. So we're starting off in this case with elastic potential energy. Really, our starting point is that we've stretched this spring, we've pulled it 12 centimeters, and then we want to know what the kinetic energy is going to be when we let it go, because we know based on the scenario and also comparing this to others we've already looked at, that once we let this go, this box is going to be moving, okay, as the spring goes back to its equilibrium position. So we're going to have elastic potential energy converted to movement or kinetic energy. So EPE is our initial state, 1/2 kx squared. And here we're not looking for velocity. We just want to know what is the maximum kinetic energy. That's going to be our final state. That is equal to 1/2 mv squared, but we don't have to solve for all of that. We're really just solving for this. Okay. So let's put some numbers in. We've got 1/2 times 2,500. That's our spring constant times 12 centimeters. I got to convert that to meters. So that's going to be 0.12 squared. That should give me my final kinetic energy. Okay. Or my maximum kinetic energy. And I can simplify this out. 1/2 times 2,500 times 0.12 squared gives me 18. And that is one of my choices. Yay. 18 joules. So that's my maximum kinetic energy for this situation. Because I'm going to have my maximum kinetic energy as soon as I let go of that spring and that box starts moving. Okay. The last couple of questions, they're not so much on springs. They're more AP topic questions that I wanted us to look at. But they're related to energy. So we've got an amusement park ride. So this is our ride. We've got two identical carriages. They revolve around the center. They travel at a constant tangential speed. Okay, so they're like a uniform circular motion ride where these are moving at the same velocity value, okay, as they travel around and around. And we want to know at what position is the total mechanical energy of the cart, earth, so cart, and earth system at its maximum value. Okay. So this one, you might get tangled up in trying to analyze each of these different situations. Here we've got one where the carriages are on top and bottom. Here they're kind of, I don't know, at an angle, I guess. And then here they're horizontal to each other. And then our last choice is the total energy is constant. If we're thinking about conservation of energy, okay, we're going to remind ourselves this is a system. They have not mentioned any other external forces acting or friction or anything like that we've got to consider. Okay. And then we can also remind ourselves a couple of other things. Okay. They tell us that we have a constant tangential speed. That means our kinetic energy is going to be constant because we're always going to have the masses are going to stay the same. The velocity value, or at least the magnitude of it, is the same. Okay, so KE remains the same. And then if we're looking at a cart earth system, at any point, these two carts are really going to offset each other in terms of height. So this one might have a max gravitational potential energy here, but this one is going to offset it. Same here, okay? This height offsets this height. These are the same height, okay? At any point, that gravitational potential energy of the whole system is going to be the same, no matter where you look. Even when the carts are in different positions, they're offsetting each other. And this is a question where you can put numbers in if you don't believe it. I did work that out. So if you look at the key, you'll see that I made up some numbers for the masses of the carts and for velocity and for some heights. And I tried out mechanical energy for a couple of these, and I got the same value. This is going to come back to conservation of energy. So we said kinetic remains the same because velocity is constant value. And then potential energy, each cart offsets the other. So that remains constant. So we're going to end up with, our choice is going to be D. My total energy is going to remain constant. And that's like my mechanical energy. Okay, my sum of my kinetic and my potential at any point is going to be the same, because this is a conservation of energy system. If they told us that something, there was some kind of work being done on this, or there was friction or something else happening, then we wouldn't be able to make those assumptions. And again, if you look at the key that I'm posting for the homework, you'll see some more worked out that I'm just not doing it all here in the interest of time. But you can make up some numbers for your carts and your height and your velocity and try it at these different points and see that you end up getting the same numbers each time for mechanical energy. Okay. All right, last one, another AP topic question, again on energy conservation. We've got an object of mass m. It's attached to a string. The string mass is negligible, so we don't care about that. Spun in a vertical circle of radius r. Okay. As the height increases, the speed decreases, such that the object, so this is the object that's being spun, Earth system's total mechanical energy remains constant. So we want to know, by how much does the kinetic energy decrease when we move from point O, which is the lowest point, to point P? Okay. So reminding ourselves, kinetic energy equals 1/2 mv squared. Potential, gravitational potential, or UG, is mgh. How much does the kinetic energy decrease? So if we're thinking about conservation of energy, okay, for my object, at this point, it's going to be at its highest. So it's going to have its max gravitational potential here. At this point, it's going to be its lowest, and it's going to have max kinetic energy here. It says that as the height increases, its speed decreases. And then I'm imagining what has to happen is that as it comes back down, its speed is increasing, offsetting the lack of height. Okay, so that total mechanical energy remains constant. So how much does the kinetic energy have to decrease from this point to this point? If this is our max kinetic and this is our max gravitational potential, then it's going to have to decrease by the max gravitational potential amount to go from this lowest point to this highest point. Okay. So decreases by max UG amount. Okay. And my max amount for UG is going to be, I'm going to use m times g times h. Okay. I'm told this has a mass of m, so I've got big M, and then I've got g. And then as far as height goes, okay, this is a circle, so my height is really going to be the diameter of this. I'm told it has a radius r, so my diameter would be 2 times r. And so looking at my choices, do I have one that expresses all that? Yes, I do, right here. Okay, so that is going to be my answer. It's really, this one again, it seems confusing and complicated at first, but then as you look at it more, you realize it's really just energy converting from kinetic at the bottom to potential at the top. Okay, and then it would convert back from potential to kinetic as it goes to the lowest point, and then continue in that, continue in that pattern as long as it's being spun in the circle. So, okay, so that is all the homework for this week.